So once again, welcome back, my dear students. Today we are having a lecture number 3 for the thermodynamics. Till the last lecture, we have completed this reversible and irreversible process, lecture number 2. So that time I told you, reversible process means here once again I am telling you equilibrium. It is an equilibrium when you removed a small weight, then a small change in pressure, and here also a small change, pressure reduced inside also, then again equilibrium. So each and every step is in equilibrium with previous one. Here final and initial equilibrium is there in the case of irreversible reaction. Okay. So now the third lecture of this thermodynamics and topic is heat. What is heat, children? Sorry. So heat is, you can say, energy exchange between system and surrounding. Energy exchange between system and surrounding. Sometime you will get the sounds of chirping of birds because here sounds is coming. Energy exchange, what I written here, energy exchange between system and surrounding. Okay, you can say heat is form of transfer of energy. It is a form of transfer of energy. Okay, so heat flow from which temperature to which temperature? Higher temperature to lower temperature. So here what is written? From form of transfer of energy, that is your heat. When there is temperature different, when there is temperature difference. If temperature difference is not there, then it is not possible. If temperature difference is there, then only it is possible. So simple thing, symbol of heat, that is capital Q, unit it is joule, Joule, but joule it's called. But the common unit is calorie. Okay, 1 calorie is equal to 4.182 joule. So it is a form of transfer of energy. Okay, so here children, heat given to the system, this you have to remember always, heat given to the system. If heat is given to the system, then what happened? System is getting energy, then system will be positive. Then heat given by the system, that means system is providing energy to someone, then system will get negative charge. It is just simple thing. If you are providing some energy to other person, then you will be negative, and if someone is providing you energy, then you will be positive. That's it, simple thing. Now the thing is specific heat capacity of gas. Specific heat capacity of gas. So it's a very simple, children. What is the formula? Specific heat, symbol C, Q upon M delta T. So what will be the definition? In that case, you can write what you can write for 1 gram of substance, for 1 gram of gas, you can say, because we are talking about gas. For 1 gram of gas, to raise the temperature by 1 degree Celsius, for 1 gram of gas to raise the temperature by 1 degree Celsius, required heat is C, specific heat capacity. See, you can check it. This is your Q. Q means what? Heat. M means mass. Mass means 1 gram. T means difference in temperature. Difference in temperature. So, for 1 gram of gas to raise the temperature by 1 degree Celsius, required heat energy is your specific heat capacity. Okay. So this is the thing. It is one example I am giving you, then it will be more clear. C is equal to 4.2 joule gram degree Celsius. It is a specific heat capacity of water. What is the meaning of this? That means 1 gram water. For 1 gram water, if you want to raise the temperature 1 degree Celsius, then required amount of heat is 4.2 joule. 1 gram water, raise the temperature by 1 degree Celsius, then required heat is 4.2 joule. That is the meaning. Okay. So now I am removing it. Check it. Specific heat capacity of gases we are talking. So suppose for isothermal process, means, children, T constant. If T is constant in this formula, then what is delta T is equal to 0. Delta T is equal to 0. Then something upon 0, it will be infinite. So here C will be infinite. So in the isothermal process, specific heat capacity is infinite. Now to adiabatic process. See what happened in adiabatic process. Check it. Adiabatic means Q is equal to 0, no heat exchange. Then here Q 0, 0 upon something 0. So here specific heat capacity is 0. So that means the thing is specific heat varies from 0 to infinite. That's the thing I want to tell you. Okay. So two kind of specific heat capacities are there. Two specific heat capacity. Which are these two? Number one, specific heat capacity at constant volume. Specific heat capacity at constant volume. SHC. HSHC, specific heat capacity at constant volume. It will be represented CV. It's a small CV. Q upon M delta T. That CV, what you are thinking, it is not that CV. It's a specific heat capacity. Q upon M delta T. What is the meaning? Constant volume. Constant volume means 1 gram gas. You want to raise the temperature 1 degree Celsius. Then required heat is your specific heat capacity at constant volume. So mass is 1, temperature is 1. So from here you will get CV is equal to Q. CV is equal to Q. Second part is SHC, specific heat capacity at constant pressure. So it is CP. CP is equal to, it is not that CP, okay? I will tell you that also, so no need to worry. It will be again CP is equal to Q. Here also same value will come. CP is equal to Q. So what is the difference here? The difference is, children, the difference is so constant volume. These are the small Cp and Cv. These are the small Cp and Cv. Unit, if you are talking about unit, then unit is what? Joule gram degree Celsius. Joule gram degree Celsius. Now, molar specific heat capacity that we have to discuss. That is the important. Molar specific heat capacity. I am not writing full. Molar specific heat capacity. What is this definition? Simple. The amount of heat required to raise the temperature of 1 mole of a gas by 1 degree Celsius. So the only difference is here, that time we are talking about 1 gram and here we are talking about 1 mole. So it's a molar. Similarly, molar specific heat capacity at constant volume. Molar specific heat capacity at constant volume. So it is now capital Cv. Again, formula is Q upon N delta T. M replaced by N because here we have to use number of moles. Then second, same, molar heat specific heat capacity at constant pressure. So Cp is equal to capital Cp Q upon N delta T. Okay. So let's check one example. So what is that example? They have given one example, O2 gas. For O2 gas, Cv, small cv is x, then find capital Cv. So small cv is what, children? 1 gram, and capital Cv 1 mole. That is the difference. Small cv means for 1 gram of O2 to raise the temperature by 1 degree Celsius, required heat is your Cv, small cv, and capital Cv for 1 mole. Okay, so Cv is given x. So O2 means what? 1 mole. 1 mole means 32 gram. So if Cv is x, then capital Cv will be 32x. So from here one conclusion came, capital Cv is equal to molar mass into small cv. Capital Cp is equal to molar mass into small cp. That is the conclusion. If a small cv is given or a small cp is given and capital Cv they are asking, then multiplied by molar mass. Okay, so this is all. Now the very important discussion, important relation. What relation? Cp minus Cv is equal to R. Capital Cp, capital Cv is equal to R for any gas. Till the first law of thermodynamics, we'll talk about the gases only. Okay. In that case, one question is given, for N2, the value of small Cv is what? 4 options are given: 14R, R by 14, 28 R upon 28. See how to solve. Capital CB is equal to R. Capital CP is what? Molar mass into CP minus molar mass into CV, small cv is equal to R. Molar mass common, small cv is equal to R. So small cv is equal to R upon M, and molar mass of N2 is what? 28. So last option will be correct. So from here more formula you can form, like Cp is equal to Qp upon N delta T, Cv is equal to Qv upon N delta T. Then from here Qp is equal to Cp is equal to Qp, Cv is equal to Qv. So Qp is equal to N Cp delta T. Similarly Qv is equal to N Cv delta T. So these are the formulas. Formula. One more thing, Cv is equal to F upon 2R. That is the value of Cv. What is F? Degree of freedom. Degree of freedom. What is degree of freedom, children? Degree of freedom means any gas, how can it move? How can it move? See, suppose here x-axis, y-axis, z-axis. Any monoatomic gas like helium is placed, so it can move in x-axis also, y-axis also, z-axis also. So how many total ways of movement? 3. So 3 will be the degree of freedom for monoatomic gases. So degree of freedom depends upon the atomicity of gas. Okay, so monoatomic gas like neon, argon, etc. Degree of freedom is 3. Diatomic gas like O2, N2, etc. Degree of freedom is 5. Okay, and number 3, polyatomic, CO2, O2, O3, etc. Degree of freedom is 6. That is enough for you. You have to learn this value. So if you know the Cv value, then you can easily find out Cp. So Cp is equal to R plus Cv. So Cp is equal to F by 2 plus 1 R. That is the value of Cp. Okay, the Cp and Cv is clear. After Cp and Cv, one more value come, gamma. Gamma is ratio of Cp and Cv, Poisson's ratio. Gamma is ratio of Cp upon Cv. Okay, so let's see. Almost video is going to complete. I will take 5 more minutes. Here one table I am going to discuss. F Cv is equal to F by 2R. Cp is equal to Cv plus R, and gamma is equal to Cp upon Cv. Check it. Monatomic. Then F value 3. So Cv is equal to 3 by 2 R. Cp is equal to 5 by 2 R. Gamma is equal to 5 upon 3, which is 1.66. Diatomic. F value 5. Cv is equal to 5 by 2 R. Cp is equal to 7 by 2 R. Gamma is equal to 7 upon 5, 1.4. Then polyatomic. Cv is equal to 3R. Cp is equal to 4R. Gamma is equal to 4 by 3, 1.33. So here what you have to remember always, children, the very important thing, which is gamma value for monatomic is always more than gamma value for diatomic, then gamma value for polyatomic. So the values are 1.66, 1.4, and here 1.33. It is always one formula. Also you can use gamma is equal to 1 upon 2 by F to find Poisson's ratio. Okay, so my dear children, my dear students, this is all about this video number 3. Hope you enjoyed the video. So this side your chemistry mentor Govind Govind sir. I hope you people are taking benefits of these videos and preparing your competitive exam well. Thank you.